Swayam Prabha. Digital India. Educated India.
So can I replace the resistor with something else without changing any of the branch voltages or branch currents in the circuit N? So please try to answer this. I am not getting any responses. So because of the setup here, I will not be able to hear your questions over audio. So somebody has raised their hand, but please use the chat window to ask your question. Okay, I've got only one response which says that this could be replaced by a voltage controlled current source. Now I'm not sure what is the intent of this answer. Perhaps it means that we have seen that a voltage controlled current source can behave as a resistor if the controlling voltage happens to be across the current source. Okay. Now this is not my question really. I mean, this is fine, this is true, but this is a resistor. Okay, a voltage controlled current source with the controlling voltage across the current source will be exactly the same as a resistor. So my question was, can we replace it by any other element? And somebody said a voltage source. Okay, now that is possible. We'll see how. Now it turns out that a resistor can be replaced with either a voltage source or a current source of specific value. Okay. Now please understand that this will not work in general. That is, you have a circuit N with some particular value of sources inside. Okay. So under those conditions, you will have some particular current and particular voltage across this resistor. So in that condition, you can replace this with a voltage source or a current source. Now if you change the sources inside N, they will not be the same anymore. Okay, they will be the same only for a particular value of the sources inside the network. Okay, now let's see how we can prove this. The proof is very simple, and it involves no algebra, just some simple logic. Okay. Is there a problem with the audio again? Okay, so it looks like things are working. So let me copy over this circuit. Okay. Now, as I said, for particular values of some sources inside, this could have any number of resistors, voltage sources, current sources, even control sources, and so on. And I am showing one particular component here. We could do this with more than one component. Now, for this set of values, there is a current IR through the resistor and a voltage VR across the resistor. Okay. Now, let me do this. What I will do is, I will connect a current source of value IR in this direction and another current source of exactly the same value IR in the other direction. Okay. So I have connected two equal and opposite current sources, which means that I have not really connected anything. Okay, because the current here will be exactly 0. Right? All I did was there is nothing connected here, and that nothing I represented as a parallel combination of two equal current sources in opposite direction. The value of each current source I took to be the current flowing in the resistor. Okay. Now what I will do is I will just interchange the positions. Okay, you see that this resistor, this current source and that current source are in parallel. I will put this current source on the left side and the resistor in the middle. Okay. This is IR and across this we have VR. And the current through the resistor will be exactly the same as before, because nothing has really changed. Okay, from my original circuit I have not made any changes. I added a net of 0 current here, and then here I just simply changed the way I drew the circuit. Okay, but the interesting thing now is, what will be the current in this part of the wire, this part of the circuit, this wire? Let me show that in blue. What will be the current in these blue wires? Okay, I think all of you can immediately recognize that this current is 0. Okay. So now if a wire is carrying 0 current, there is no point having that wire. I may as well cut it off. Okay. So this current will be 0. So I can cut this off and nothing will change in the circuit. Okay. Because whether I have an open circuit, that is a cut wire, or a wire with exactly 0 current, it is exactly the same thing. Okay. So it won't disturb the circuit. So I can cut off those things. So what is the bottom line here? My original circuit was like this, and after I did all the transformations I described to you and cut off this wire, my circuit is like that. And all through the steps of logic we saw that nothing really changes in this circuit. So the voltages and currents in this circuit will be exactly the same as the voltages and currents in that circuit. Okay. So what this means is that a resistor with a current IR flowing through it can be substituted by a current source of value IR, and in the appropriate direction, of course. IR is flowing downwards here, so this current source has to point downwards. Okay, and this will be without changing any branch voltages or currents. Okay, I hope this is convincing, and this particular result is known as the substitution theorem. Okay, so this, it turns out, is quite useful in many applications. I mean, when I say applications, to solve other problems and maybe prove other circuit theorems. Okay, so is this convincing? Any questions about this chain of reasoning and the proof of substitution theorem? Okay, so now we can also quickly go through another possible substitution. What I will do is, previously I added zero current, and that zero current I represented as IR, two current sources of value IR in opposite directions in parallel. Okay, now what I will do is, in series with this particular wire, I will break this wire. Okay, and add two voltage sources of equal and opposite value, and the value I choose to be VR. And what is VR? Whatever voltage was across this resistor. Okay, so now clearly this voltage will be the same as that voltage, and essentially this combination, two equal and opposite voltage sources in series, it's nothing but a short circuit. Okay, so nothing has changed in the circuit. Now with respect to some reference voltage, let me know, let's say, let me call this, I formed a new node here, let me call this N1 and N2. How will the voltage at N1 be related to voltage at N2? Okay, so maybe I will say the value of Vn1 minus Vn2, that is the voltage at N1 minus the voltage at N2. What is this value going to be? Please try and answer this question. My question is, how is this voltage related to that voltage? Okay, now I think it must be pretty convincing to you that I have not changed the circuit in any way. All I did was to connect 0 volts in series with the wire, which is like not disturbing the wire at all. But that 0 volt is represented as two equal and opposite voltages of value VR in series with each other. Okay. So they will be at the same voltage. Again, this is pretty clear. If you go from here, you have a voltage rise of VR and a voltage fall of VR. So these two will be at exactly the same voltage. Now given that they are at the same voltage, what I can do is connect them up like that. Okay. So my circuit becomes, I will redraw it slightly differently. I'll have VR across this, okay, and you have something hanging from here which is VR and this resistor, but you can see again that the current in this wire is definitely going to be 0, okay, so that part can be removed from the circuit. Okay, so what we have done is that the resistor which was across these two terminals has been substituted by a voltage VR, where VR is the actual voltage across the resistor in the circuit. So this is another variant of the substitution theorem. If you have a resistor with a voltage VR across it, it can be substituted by an independent voltage source of value VR without changing the circuit solution. Okay, is this fine? So this is another variant of substitution theorem. So in summary, what it says is that if you have a circuit with a resistor R which has a voltage VR across it and a current IR through it, you can substitute that resistor by a current source of value IR in the appropriate direction, or a voltage source of value VR in the appropriate polarity, and the circuit solutions will be exactly the same. That is, the branch voltages and currents here, here and here will be exactly the same. Okay, and this is known as substitution theorem. Okay, any questions about this? Any questions about the statement of substitution theorem or the proof? Any questions? Okay, so let's move forward. Now, one thing I want to point out is we took a resistor and then substituted it. First of all, you can do this for multiple resistors in a circuit. It doesn't have to be only one, and also it doesn't have to be a resistor. It can be any element. Okay. So instead of a resistor, we could have any element, okay, which has a current IR through it and a voltage VR through it. I will still call it IR and VR. This need not be a resistor. This can be any two terminal element. Okay. And also, when you say any two terminal element, that itself can be a complicated network with only two terminals exposed. Okay. So this could be another network. The only condition is that only two terminals are brought out like this and they are connected, and this entire thing can be substituted by, let's say the voltage across these two terminals is VR and the current flowing that way is IR, and this entire thing can be substituted by a current source of value IR or a voltage source of value VR. Okay. So I started with a resistor, but you can work out for yourself that the logic of the proof holds good even if it is a nonlinear element. It can be any element. In fact, you can substitute a voltage source by a current source and vice versa. And also you can substitute a complicated circuit as long as it is only at two terminals. Okay. So if you have a complicated network with only two terminals brought out, you can substitute the entire network by this voltage source or current source. Okay. I hope that part is clear. So there is a question asking about, is there any limitation of this theorem? I mean, there really is no limitation. The only thing is this theorem by itself is somewhat limited in that it works for specific values of voltages and currents. I will take an example, after that it will become clear. But like I said, there is no other limit. You can replace any element with a voltage source or a current source. Okay. And when I say element, it can be a simple thing like a resistor or some nonlinear element like a diode. But it can also be a complicated network. Okay. So as long as only two terminals are brought out, it doesn't matter what the network is inside. It could have thousands of components, but at those two terminals it can be replaced by either a current source or voltage source. But this current source and voltage source are not arbitrary things. They are the actual currents or voltages flowing in the original circuit. Okay. So I hope that is clear, and that also kind of summarizes the substitution theorem which someone else asked for. And as far as the application of this is concerned, in fact we will see shortly, we will prove other theorems using this theorem. Okay. So, and there is a question, what is superposition theorem? Superposition we have discussed earlier. Okay. We saw that we proved it with the nodal analysis, but you can do it with any which way you want. The unknown vector in the nodal analysis method will come out to be G inverse times the source vector. Okay. I call this I and V, but we know that this can contain independent current sources and voltage sources. Okay. So let's say this independent source vector had two current sources, I1, I2, and many zeros, and then a voltage source also. Okay. So this is the same as what I am writing now. So this is the solution to the node voltages to the unknown vector when all sources are acting together. Now this is the solution when I1 is active and other independent sources are set to 0. Similarly, the second one is when I2 is active and other independent sources are set to 0, and this finally is when only V1 is active and other independent sources are set to 0. So this is superposition theorem. What it says is, if you have a number of independent sources in a circuit, the solution when all of them are active can be obtained as the solution sum of solutions when each one is active and all the others are set to 0. Okay, so that is, you can activate the sources one by one and set all the other sources to 0. In this case, you first do the analysis with I1 only and I2 only and then V1 only and add up all the solutions, and this works for any circuit that is linear. Okay. And a linear circuit means it has, besides these independent sources, it has resistors and linear controlled sources. Okay, so this is superposition. Okay, so I hope that part is clear. Now let's take a numerical example also to illustrate substitution theorem and to get a bit of practice with circuit analysis. I will take a very simple circuit. Let's say it has a single source, 16 volts. Okay, so now what I would like you to find are these quantities. Please don't do it right now. In fact, you have to do a little bit of working out. This circuit is not very difficult, but you still have to do that. So please take it as an exercise and do it before next Tuesday, and we'll discuss this circuit and how to solve it in the lecture. Okay. So please calculate the voltage across this. I'll call that V1, and the current through this resistor, I'll call that I2, and the current through this resistor, I'll call it I3. Okay. Calculate V1, I2, I3, and you can also calculate V3 here across this. Okay.